Before we dive into the depths of this atomic revolution, let's map out the territory. The transition to 2 nanometers technology is not a mere incremental step. It is a total overhaul of the semiconductor industry. Our journey begins with the end of scaling, where Moore's law hits a physical wall, forcing us to move from shrinking to reinventing. We then explore density beyond imagination, looking at how we pack billions of transistors into spaces smaller than a fingernail. This leads us to the impact on mobility, where battery life and performance finally stop being a trade-off. We will pull back the curtain on the invisible upgrade, explaining why your future devices will feel magical rather than just faster. We'll witness the global race between titans like TSMC, Samsung, and Intel, a multi-billion-dollar chess game with geopolitical stakes. We will see how this technology cascades from premium to ubiquitous, moving from the hands of the elite to the pockets of the masses, and how its ripple effects transform everything from self-driving cars to the data centers that power our world. Finally, we look at the AI catalyst, where 2 nanometers chips become the brains that allow artificial intelligence to live locally on your device, and how this lays the groundwork for the quantum era innovations of tomorrow. This is the new chapter in computing. For 50 years, the tech industry followed a predictable rhythm known as Moore's law. The number of transistors on a microchip doubles roughly every 2 years. It was a golden age of simple scaling. If you wanted a faster computer, you just shrunk the components. But as we approached the 3 nanometer and now the 2 nanometer threshold, we hit a wall. When you get this small, electrons start to behave strangely. They jump through walls they shouldn't be able to cross, a phenomenon called quantum tunneling. The 2 nanometer shift represents the moment we stop fighting physics and start dancing with it. We are no longer just printing circuits. We are manipulating matter at the atomic level. A 2 nanometers transistor is significantly smaller than a single strand of DNA. To build something this small requires extreme ultraviolet EUV lithography machines that cost hundreds of millions of dollars and use lasers to create light so precise it can carve patterns on a scale previously thought impossible. This isn't just refinement. It's a break from the past. Designers can no longer rely on the old blueprints. Every aspect of the chip, the way power flows, the way heat is dissipated, the way signals are sent, must be reimagined. We are entering an era where the architecture of a chip is as much about philosophy and physics as it is about engineering. Imagine a city block. In the 1990s, that block had 10 houses. By 2010, it had a dozen apartment buildings. In the 2 nanometers era, that same city block is now a vertical forest of interconnected megastructures, housing millions of residents in the same physical footprint. This is what 2 nanometer technology does for transistor density. By utilizing new transistor structures like the GAAFET, gate-all-around field effect transistor, engineers can wrap the gate, the switch, around the channel, the path for electricity, on all 4 sides. This allows for unprecedented control over the flow of current. The result? We can pack billions more transistors onto a single chip. Why does density matter to you? It means computational overhead. It means your device can do more things simultaneously without breaking a sweat. When density increases, the distance electricity has to travel decreases. This micro-level efficiency translates into macro-level power. We are talking about computing potential that pushes beyond what we previously perceived as physical limits. We are essentially fitting a supercomputer from 10 years ago into the sensor of a wearable ring. We have all felt the battery anxiety, that moment when your phone hits 15% in the middle of a busy day. The 2 nanometer revolution is the cure. Because 2 nanometers transistors are so small and the current control is so precise, they require significantly less voltage to switch on and off. In the world of 2 nanometers, efficiency is the key word. We are looking at a future where your smartphone doesn't just last a day. It might last 3. But it's not just about battery life. It's about thermal management. Heat is the enemy of electronics. When chips are inefficient, they get hot, and when they get hot, they throttle or slow down to protect themselves. 2 nanometers chips run cooler. This means that tasks once reserved for a liquid-cooled desktop PC like high-end gaming or 3D rendering can now be performed on a handheld device without it burning your hand. This transforms mobility from a compromised experience into a primary experience. Your phone isn't just a communication tool anymore. It's your most powerful workstation. The most profound technological changes are the ones you don't notice. This is the invisible upgrade. When you pick up a 2 nanometers powered device in 2026 or 2027, it won't necessarily look different. It might be slightly thinner or lighter, but the real change is in the friction. Think about 8K video editing. Today, it's a chore that requires a high-end Mac or PC. With 2 nanometers, you will be able to edit and export 8,000 video on your phone as easily as you post a text message. Consider real-time augmented reality, AR. For AR to feel real, the digital overlay must sync perfectly with your head movements. Even a millisecond of lag breaks the illusion. The speed of 2 nanometers processing removes that lag, making the digital and physical worlds blend seamlessly. This is technology that feels intuitive. It's the magic of a device that anticipates your needs, processes your voice commands instantly, and renders graphics so lifelike you forget you're looking at a screen. It's an upgrade that removes the wait time from our lives. Behind every chip is a massive industrial machine. The race to 2 nanometers is arguably the most expensive and high-stakes competition in human history. Three titans, TSMC, Taiwan Semiconductor Manufacturing Company, Samsung, and Intel, are locked in a battle for supremacy. TSMC is currently the king of the mountain, supplying giants like Apple and Nvidia. Their move to 2 nanometers is a massive logistical undertaking, involving the construction of new gigafabs that cost upwards of $20 billion each. Samsung is fighting back with its early adoption of GAAFET architecture, hoping to leapfrog the competition by mastering the most complex designs first. Intel, under its IDM 2.0 strategy, is racing to regain its crown, investing heavily in US-based manufacturing to ensure they aren't left behind. This isn't just a business story. It's a geopolitical one. These chips power everything from smartphones to fighter jets. The country that masters 2 nanometers first gains a massive economic and strategic advantage. When you hold a 2 nanometers device, you are holding the result of a global struggle for the future of the 21st century. Innovation always begins at the top. The first 2 nanometers chips will undoubtedly debut in the most expensive flagship smartphones, the Pro Max models and the Ultra editions. They will be the playthings of early adopters and tech enthusiasts. However, the history of silicon shows us that today's premium is tomorrow's baseline. As manufacturing yields improve and costs go down, 2 nanometers technology will cascade. Within a few years of its debut, the same processing power will be found in budget phones, student laptops, and even smart home appliances. This democratization of power is what actually changes society. It's not when the CEO gets a 2 nanometers chip that things change. It's when the student in a developing country gets one. When high-performance computing becomes ubiquitous, the floor of human potential is raised. Everyone gains access to better tools, better education, and better connectivity. While we often focus on phones, the 2 nanometers revolution will be felt most deeply in sectors we rarely think about. Autonomous vehicles. Self-driving cars are essentially supercomputers on wheels. They have to process millions of data points per second from cameras, LiDAR, and radar. 2 nanometers chips allow for smarter processing with less power draw, which is vital for electric vehicles where every watt counts. Data centers. The internet runs on massive server farms that consume staggering amounts of electricity. Moving to 2 nanometers allows these data centers to do more calculations while using less power and generating less heat, making our digital lives more sustainable. Wearables. Imagine a smartwatch that can monitor your blood glucose, your EKG, and your stress levels in real time, all while lasting a week on a single charge. 2 nanometers makes the medical-grade wearable a reality. We are currently in the middle of an AI boom, but most of it happens in the cloud. When you ask a chatbot a question, your data is sent to a massive server, processed, and sent back. This creates latency and raises serious privacy concerns. 2 nanometer chips are the catalyst for on-device AI because these chips are so efficient and dense. They can run complex large language models, LLMs, locally. Your phone will be able to translate languages in real time during a conversation without an internet connection. It will be able to analyze your private health data without it ever leaving your device. This makes AI faster, more reliable, and most importantly, more trustworthy. The 2 nanometers era is the era where AI stops being a service you use and starts being a feature of your hardware. Perfecting silicon at the 2 nanometer scale is perhaps the final frontier of traditional computing, but it isn't the end. By mastering the manipulation of atoms at this level, we are building the bridge to what comes next. The manufacturing techniques developed for 2 nanometers, the extreme precision, the new materials, the vacuum-sealed environments are exactly what we need to build quantum computers and neuromorphic chips, chips that mimic the human brain. We are currently learning the language of the universe at its smallest scale. The breakthroughs of today are the GAAFET, with which we will write the future of the 2030s and beyond. We have reached a decisive shift in history. The move to 2 nanometers is not just a speck on a box. It is a fundamental redefinition of what a device is. We are moving away from tools that we use and toward technology that is integrated into our very existence. Smaller, faster, and more efficient silicon means that the boundary between the digital and the physical is dissolving. As we rebuild our computing world atom by atom, we are also rebuilding our potential. The 2 nanometers revolution is a testament to human ingenuity, our refusal to accept the physical limits of the world and our drive to always find a way to go further. As we enter this new era, how should you navigate it? Value efficiency over specs. When you look for your next device, don't just look at speed. Look at performance per watt. The 2 nanometers era is about how much a device can do with a little, not how much it can do with a lot. Prioritize on-device privacy. As 2 nanometers enables on-device AI, look for companies that prioritize local processing. Your data is your most valuable asset. Keep it on your hardware. Invest in longevity. 2 nanometers technology represents a significant leap. A device bought at the start of this era will likely remain current and capable for much longer than previous generations. It's worth waiting for the right leap. Stay curious but grounded. Technology is a tool, not a destination. Use the power of 2 nanometers to enhance your life, your creativity, and your connections. But don't forget to look up from the screen. The 2 nanometer journey is a reminder that we are living in a sci-fi novel written in real time. But with great power comes great questions. If your phone could process anything instantly without the cloud, what is the one thing you would want it to do for you? As AI moves from the cloud to your pocket, do you feel more or less secure about your privacy? Are we approaching a point where technology becomes too fast, or is there no limit to our need for speed? I'd love to hear your thoughts in the comments below. Let's start a conversation about the invisible world that's about to change everything. I wish you all great health, abundant energy, and the wisdom to use these new tools to build a better future. If you enjoyed this deep dive into the atomic frontier, don't forget to subscribe to the channel and hit that notification bell. We have many more stories to tell about the future of humanity and the machines that power it. Until next time.